Okay, welcome to lesson 25. We're going to finish up intro to hypothesis testing because trust me, this is just tip of the iceberg here. We're going to talk about our conclusions. So we hinted at it already. And then we are going to put our conclusions in two-part conclusions. So we had a two-part confidence interval conclusion. Conclusion. And we had a two-part hypothesis test conclusion. The four-part conclusion is just combining them together. And then we're going to talk about types of error. That can be a little fun sometimes. We're going to talk about some limitations and have a comparison to hypothesis testing and confidence intervals. So, like I said before, you're absolutely going to want to highlight this slide. It's a two-part conclusion here. So there's the first part where you tell us whether or not you reject or fail to reject the null. Sorry. You give us a p-value. A lot of times it's quite normal to give the test statistic as well. And then you include the significance level. Then you tell us how strong the evidence is for the alternative in context. Okay, so stating our conclusion in terms of the alternative, you want to be careful. Reject, fail to reject, do not throw that into a thesaurus. It will not be marked correct. And it's a lot easier, like I said, I mentioned I think probably at the end of lesson 24, to say, hey, there is blank evidence that the alternative is true. It's a lot easier than saying against the null. The second way makes you use a lot of double negatives. It's real gnarly. So we're going to use this spectrum here. So it's very strong or convincing. The smaller our p-value is. Strong, moderately strong, right around 0.05. But then anything higher than 0.10 is really weak. So we'd say little to no. I've seen people write there's no evidence. I tend to avoid that because we don't like absolutes. It sounds like there's, the p-value 0 or 1. We, in fact, rarely, we don't want to round our p-value to 0. Because a p-value of 0 means that what you saw in your sample is literally impossible. But if you saw it in your sample, clearly it's not. So if your value is really, really small, we're much more likely to say p-value less than, and then a small number like 0.001 or 0.0001. R has some default, it gives you, it's like 2 point something times 10 to the negative 16th. I don't know where it came up with that number, but something like this is fine. So in terms of the train problem, so given a p-value of 0.006, I think we had 0.0062, there's very strong or convincing evidence that the average train ride time on this train for all trips between Rome and Florence is longer than 94 minutes as advertised. So writing the four-part conclusion here. So this is where we go ahead and we put the two-part conclusion for a confidence interval and combine it with a two-part conclusion for a hypothesis test. That was just my cat's automatic feeder. I had to pause the recording because she always runs across the room. It's delightful. So it doesn't matter what order the parts are in, but it does matter that all of them are there. We have a checklist of statements that we're looking for. If any of them are missing, that's what we hone in on. So for here, So 4 parts. So whether or not we reject and why. We state how strong the evidence is for the alternative. And then we give the confidence interval as well as the point estimate. So the point estimate's one of the... So here are the two for the hypothesis test. Here are the two for the confidence interval. So if we wanted to just put them together, sorry, they might come in out of order. So we reject the null hypothesis with a p-value of 0.006 as significance level 0.05. I did include this Z statistic there. There is, very strong or convincing evidence that the average ride time between the two cities on this train is longer than the advertised 94 minutes. We didn't do this particular part in the slides, but feel free to check them. The 95% confidence interval for the average train trip time for all rides between the two cities is 95.1 minutes to 102.9 minutes with a point estimate of 99 minutes. So this is just X bar from the sample. So that would be my 4-part conclusion. And you'll see on the data analysis for this week, we will ask for a 4-part conclusion. We are looking for all of these key points. So just keep in mind, and context is super important. If you leave out the context, that is worth a good chunk of it, because this is the part where you translate it to where a client can read it. Or you, even. If you want to read it 2 weeks later, you need to be able to read it and know what it's about. It's very, very difficult if you write it up in technical stats jargon and don't write the context, like that it was about trains, that kind of idea. Oops, so just a comment. It looks like the commuter's hunch has some merit. Because if you look here, this entire confidence interval is above the 94 minutes. So absolutely, this commuter's onto something. Maybe they should be right to be angry that, no, I'm late based on what your advertised time is, kind of idea. So errors in hypothesis testing. This one can be fun. So, and we'll go through all of them. So when we go ahead and we go through a hypothesis test and we have a conclusion at the end, there's always that possibility our conclusion was not correct. It does not mean that we were incorrect. It just means we could be. And so there are 2 types of errors that we can make in this situation. One is tied to when we reject the null, and one is tied to when we fail to reject. So we're going to, you've got this handy bit here, there's another there. We're going to go through type 1 error and then type 2 error. And just know they're tied to each other, so if you decrease the probability of one type of error, it increases the probability of the other type of error happening. So type 1 error is rejecting the null hypothesis when the null is true. It's a false positive. So, for example, if you're looking at the court case example, finding, let me see, sending innocent person to prison. So it's that scenario where you concluded the innocent person was guilty, they go to prison. Here's another example. It's kind of fun. So if you believe by default an individual is not pregnant and the alternative is that they are, this lovely mustachioed character is not pregnant, and this doctor has incorrectly rejected the null and concluded the alternative is true and told them they're pregnant. They are wrong. So this would be type 1 error. Type 1 error only happens when you reject the null. So if you're in a situation and you've rejected the null and we ask you what type of error you could have made, type 1 error is the error that you could have made because you rejected. Type 2 error, so this is when you fail to reject. And know sometimes that we actually abbreviate this FTR, fail to reject the null when the alternative is true. And usually we're not fortunate enough to know, like, for a fact that we made type 1 or type 2 error. Just know that it's something that's always a possibility. So this would be a false negative. So this would be, in the court case, let a guilty person go free. Go free. Another example here, so we're still living with the default. You assume somebody's not pregnant. If you get enough evidence, you conclude that's not true and you go with the alternative. Well, this person, if you look, that person's very, very pregnant. But this doctor has failed to reject that the null is false. They have not rejected the null. They say you're not pregnant. They're wrong. So that'd be type 2 error. So a couple of examples here, just to kind of drill it home. This is the one that if you look up types of error, it's gonna, well, not the specific name, but the court case example is the one you'll find online. So by default, let's say a person, so in the U.S. court system, supposedly, we're supposed to say, not guilty by default. And if you get enough evidence, you'll decide the null is not true and you'll go with guilty. So I have 4 scenarios here. Here's reality. So reality here, they're guilty. And here's their verdict. So if the person's guilty and we find they're guilty, this is a correct decision. Right? So we want to be able to find someone guilty when they are guilty. Good news. If in reality they're guilty, but we conclude they're not guilty, we haven't rejected the null hypothesis. So we have made an error. We've made a type 2 error. So this is that scenario where a guilty person goes free. So, well, frowny face. We're usually not too happy about it. So then I'm going to switch up my scenarios. If the person is innocent in reality and we find they're guilty, we shouldn't be happy about this either, right? So this is a type 1 error. We have rejected the null and concluded they're guilty. And that's not the right decision here. So definitely not happy because now an innocent person goes to prison. Another way to also think about it is if an innocent person goes to prison, the guilty person also goes free. A lot of times people would debate, in this scenario, type 1 might be worse. Note that it totally depends on the scenario. Some scenarios, type 1's worse. Other scenarios, type 2's worse. It totally, it changes from scenario to scenario. And so if they're finally innocent and we get not guilty, this is a correct decision. So we're happy with those. So now I have a more extreme example. I enjoy this one. So aboard the USS Enterprise, and sorry, nobody's wearing red shirts to make it obvious. Spock has been tasked with evaluating the vitals of a crew member. So by default, they're going to go ahead, they're going to assume that their coworker is alive, because I don't know about you all, I don't want to work with anybody who assumes I'm dead by default. So alive, and I don't know, they could be collecting, I don't know, body temperature or heart rate or whatever. And so they're either going to fail to reject and say, hey, you know what, I don't have evidence they're dead. I'm going to assume they're alive. But here are some consequences. So if Spock says they're alive, we're going to try and resuscitate them. If Spock says the crew member's dead, we're going to incinerate the body. So consequences, right? So now let's go through. So reality, looking at if they're dead and Spock says they're dead, this is a correct decision. I wouldn't say we're happy because your crew member's dead and that's a bummer, but we're happy that the correct decision was made. So then if the crew member is dead and Spock says they're alive, this is a type 2 error. because they failed to reject the null. So they try to revive a dead person, which is definitely a bummer. I can't lie there. I mean, my dad was a firefighter for how many years, and he would talk about that. It's not great. So I'm just going to go counterclockwise. So if they're alive, and Spock says they're alive, this is the one where we're actually like genuinely happy, right? This is a correct decision. We revived a living person. Yay. Like we like that scenario. And so I say the most extreme for last. If they're alive, but Spock rejects this and says, no, they're dead. They've rejected the null, but they've rejected the null when they shouldn't. They've made a type 1 error. So they incinerate a living person. Uh-oh, right? Tell you what, that is absolutely not what I'm about. Pass, hard pass. So, absolutely, you've got these two errors. They have totally different consequences. Trying to revive a dead person versus versus incinerating a living person. I mean, one, in my opinion, is much worse than the other. It's definitely worth avoiding making a type 1 error. And I will throw back to this slide. I want to talk about what we mean by significance level. So, significance level. So, we set this ahead of time. We usually will give you one in the prompt, or by default, you can assume 0.05 if we don't give you one. And if we don't give you one, you can clarify with us. Send us an email saying, hey, I don't see one here. Can I assume this? And we can go ahead and say yes. We are totally fine with clarifying questions like that. So this is set ahead of time before calculating the test statistic and the p-value. Otherwise, it's like watching a race and then placing your bets. But so probability, you make a type 1 error. You set it equal, to whatever your significance level is. So usually it's like the confidence intervals where we almost always use levels of 90, 95, and 99. 90, 95, 99. Look, they add to 1 or 100%. So if you use significance level 0.10, you are going to have a lower type 1 error, but you're going to have a higher type 1 error and a lower type 2. If you go the other way, you make alpha smaller, it's going to decrease your type 1, but it's going to increase your type 2. So it's not like a directly like, oh, I decreased this one by this much, so it increases the other by that much. But just know that there is an offset. If you decrease your type 1, you're going to increase your type 2 and vice versa. So it totally depends which one is worse. So here, I'm in this Spock example. Am I cool with a significance level 0.10? What that means is, if I'm okay with a significance level of 0.10, I'm cool with 10% of the crew members that Spock says are dead not actually being dead. I'm cool with accidentally incinerating a living crew member 10% of the time. That is super high. I'm not okay with that. So what's much more likely is I'm going to go with the smallest one. 0.01, you could make it smaller. I usually don't see it smaller than 0.01. But in this case, type 1 error is really bad. So you want your significance level to be really low. Because a high significance level means that they're going to incorrectly say people are dead and living people are going to get incinerated too high, too often. So keep that in mind. Totally depends on which one's worse, where you want alpha to be. And just a reminder, you reject, if your p-value is less than or equal to that significance level. That's that threshold. Okay, so looking at errors in hypothesis testing, you might recognize this. This comes from the train problem. So the one where our null is that the mean is equal to 94 minutes. The alternative is that it's greater than. We are using alpha as 0.05. We want to know, hey, if the null is true, what sample mean is going to be the cutoff? So what value for the sample mean do I need in order to reject the null? So it's basically asking, hey, 0.05. I want to know what this value is. So what we're actually essentially going to be doing is finding a percentile. So if this is 0.05 to the right, it's 0.95 to the left. I am looking for the 95th percentile. Oops, well. So things to note. So if the null is true, mu is equal to 94 minutes. So then we also know the value here, 1.645. That actually comes from the 0.05, 90%. So you might recognize that's the z-star for a 90% confidence interval. But absolutely, you can use R to find the z score associated with the 95th percentile. If you use a z-table, it's going to be somewhere between 1.64 and 1.65. In fact, it's going to be exactly between them. So then, also sigma of x bar, just a reminder, that's that sigma of x over the square root of n. So that was 10 minutes over the square root of 25 was our sample size. So 10 divided by 5 was 2 minutes. Okay, so x is going to be, and I'm throwing this back into like, hey, finding the value of x associated with whatever percentile. So actually it's x bar. So z times sigma of x bar plus mu of x, or x bar. So we can also say that's mu of x. I'm just going to plug in, so this is 1.645 times, this is 2, plus, if the null is true, mu is equal to 94 minutes. Do some math here, so x bar is equal to 97.29 minutes. So 97.29 minutes. What this means is if the null is true, and it really is centered at 94, then at 97.29 minutes and higher as a sample mean for 25 observations, 5% of the time we're going to reject when we shouldn't here. That would be my my cutoff, which we are going to use in our second part here, looking at type 2 error. So suppose the true mean actually is 98. So we're going to say, you know what, it's not actually 94. We know now it's 98. So therefore the null is false. Find the probability of type 2 error. So I'm going to explain these real quick. So this right here, this is if the null is true, and mu is 94. The green one here, looking where it's centered, this is saying, hey, no, mu is 98. So that's where that is. And then we're going to use that cutoff that we had before. Where is it? 97.29. Probably not accurate at all. 97.29. Because remember, we established that that is the cutoff. If we get a sample mean of 97.29 minutes or higher, we're going to reject here. So here, probability type 2 error is the probability that we get a sample mean when taking sample 25 or fewer. And note, this is a little screwy. We don't hand calculate these types of errors as often. Less than the 97.29 given, and I'm just going to write this here, mu is actually equal to 98. So I am saying, hey, we're focusing on the green one. The green one's the one that's true. What's the probability that x bar is less than that? We're trying to find this area here. That's what it comes down to. So we're looking at this is equal to probability that z is less than x bar minus mu, which is 98 now, over sigma of x bar. Well, you know what, I'm going to just put equals in here. 97.29 minus 98, so I'm going to get a negative z score here, over this right here, this 2. I'm going to just rewrite it in another line. So probability that z is less than negative 0.353. So absolutely you can look at just this part and throw it into a z table, find a probability from there. From R, I used this entire thing, which is equal to 0.3613. So the probability of type 2 error, which is failing to reject when it really is higher than 94 minutes, or like 98 is when it's really 98 is, that would happen about 36.13% of the time. So yeah, if I wanted to think about probability type 1 error, type 1, that's always equal to alpha. Probability type 2, that one's a lot more complicated. You can get into beta and 1 minus beta and power, but for the most part, we're going to stay clear of that. I just want to make sure you all had this if you wanted to look through it. So other conclusion limitations here. So there are definitely things you should ask yourself when you're looking at hypothesis test results. Where did the data come from? Where were these? How were they sampled? How were they surveyed? If it's an experiment, was the treatment randomized? That kind of idea. If you have a very small sample size, a lot of times it's very difficult to confidently say, yes, this sample represents a population, which becomes very, very complicated very quickly. If alternatively you have a very large sample size, it actually helps you find like the tiniest little differences between groups. It can force you to have statistical significance, even though maybe the results aren't what we call practically significant, which we'll go into. So just know that if you force your sample size big enough, eventually you'll get a small p-value. It's kind of cheating, though, to just increase your sample size until you get significance. That is gross, absolutely. Other conditions not being met, it totally varies depending on which conditions they are. A lot of times they're going to inflate your type 1 error. So in general, though, we're pretty bummed when they're not met. So statistical versus practical, wanted to throw this out there. So we have a study. They're looking at tire treads. They have 2 treads that they're looking at. So treads are, those patterns on the tires. Obviously, I am not a tire expert. So anyway, the claim, they go ahead and say there's convincing evidence TireTread1 has a longer average life. They're looking at like mileage than TireTread2 does. The hypothesis test comparing the two had a very small p-value, p-value of 0.002. Therefore, TireTread1 is superior to TireTread2. Well, let's actually take a look. So is there anything suspicious? Well, we have to look first. So where are the data from? So they were from customers volunteered this information on the tire manufacturer website. So definitely be cautious. When you have volunteered information, you definitely need to be concerned that it might be a biased sample. Usually only people who feel very strongly one way or the other are going to put their information on there. And then the sample sizes. So it looks like we had 986 folks with TireTread1, 835 with Tread2. And look at these means. So they're both really close to 50,000 miles. One's 50,153 miles. One is 50,018 miles. That's actually pretty close. Considering they're both around 50, like a difference of 135 miles relative to the 50,000-ish that they went. It's very, very tiny difference. So, yes, when you run this hypothesis test, you do have statistical significance. But I might argue we don't have practical significance because 135 miles is not really a big difference. An estimated difference, it's a very, very small difference when your tire lives are around 50,000 on average. Another way to think about it, I did a study where I do not know what they measured these things in. It was a program instituted at a middle school PE program, and it was to boost self-esteem in teenage girls. And what they did is they went ahead, they did whatever the experiment was. I don't know what it was, and the program, but at the end, they had statistically significant results. They said, hey, you know what? Our results, we found that it significantly improved their self-esteem. Things that are important to note is they took $10 million and put this into this program. So the $10 million, and then they found, hey, there was an improvement. This is great. But when they did further analysis, they found that they estimated it improved the self-esteem about 1%. So, statistically significant, yes, but from practical significance standpoint, one thing you could ask yourself is it worth another $10 million? And if you say no, then it's probably not a practically significant difference. 1% wasn't probably enough to say, you know what, obviously we need more. Tens of millions of dollars into this. So that's what we mean there. And then last year, and this can be really, really handy, confidence intervals and hypothesis tests, they are highly related. So absolutely, you should consider like a hypothesis test with a significance level of 0.10. You can think of that as kind of going hand in hand with a confidence interval that's 90%, 5 and 95, 1 and 99. You'll note if you added them together, you'd get 1 or 100%. So when you're doing two-sided hypothesis tests, very specifically, you can pretty much say, like, if you have your confidence interval and the null value, the claimed value, is inside of the interval, you would fail to reject the hypothesis test. That you would fail to reject the null. However, if you do a confidence interval and the value is not in the confidence interval, it's outside of it, then if you perform the hypothesis test, you're going to end up rejecting the null. So we have an example of what we mean, but just know that for two-sided tests, this is always going to be true. It's sometimes true for one-sided, but sometimes not. It's a little bit trickier with the one-sided. What it comes down to is the confidence intervals we calculate, they're all what we call technically two-sided confidence intervals. We'll never mess in this class with one-sided confidence intervals. So they go with two-sided hypothesis tests. So for example, we're looking at a manufacturer of wooden boards for, I guess, construction, and they want to test a batch of boards. It's really important they're of a certain length, because if they're too short, they're going to get sent back. If they're too long, then they're going to need to get cut. So the null says, hey, the average length for all these boards is 120 inches. And the alternative is, hey, it's different than 120 inches. So the thing to note, my null value here is 120 inches. So if the 95% confidence reports the average board length to be between 118.9 inches to 119.7 inches, what can we conclude for a two-sided hypothesis test? So the question we want to ask is, where is 120? Is it in this interval right here? Is it between 118.9 and 119.7? No, it's not. It's above it. It's above the interval. Above the confidence interval. So because it's not inside, this means that we would reject the null at alpha equals 0.05. Oh no, oh that was weird. This means our p-value is smaller than 0.05. Technically our two-sided p-value, but we'll get into that another time. So because 120 inches is not in the confidence interval, the 95% confidence interval, we're going to reject at the 0.05 significance level, which is really cool. You absolutely probably could work backwards and find a more exact p-value, but that's really not what we're after. We're just trying to get you to look at the results from the confidence interval. Based on that, what can we say about the hypothesis test? So I believe there you are, the your turn examples. I did add a couple. There's the hummingbird and like college tuition at private schools. Definitely have a look at these. We are going to build a lot on confidence intervals and hypothesis tests. We are going to use them for the rest of the term. So absolutely practice and then practice some more. And I'll be looking forward to your questions. See you all tomorrow.